I would like to discuss solving nonlinear ordinary differential equations using exact methods. Nonlinear differential equations form an important class of differential equations. In fact, they're the most generic form of differential equations. Take, for example, an ODE like this with y bigger than 0. So as stated, it looks like a second-order differential equation. And it's certainly nonlinear because of the square term here. Solving this equation is not easy, and in general you have to use method of successive approximations or the method of slope fields. Let me just remark that y is a function of x here. When I say y prime, I mean dy by dx. A possible way of solving this is known as reduction of order, wherein we observe that the second order aspect is not really there if we write y prime as some function of y. Observe that I'm not writing it as a function of x but rather of y. This is an important trick because if you write y prime as a function of y, then you don't involve x in the game yet. So if I take the second derivative where prime means dy by dx, so y double prime means dy prime by dx, that just becomes dp by dx. But since p has been assumed to be a function just of y, by the chain rule I can write this as dp by dy times dy by dx, because y does depend on x. Dy by dx, however, is simply p as a function of y. So this is p times dp by dy. So by this interesting looking trick, we have reduced the order of a second order differential equation to the first order form. Now the differential equation becomes y times p dp by dy plus p squared equals 0. What I can do is divide both sides by p squared, assuming that it's not equal to 0. I'll talk about what happens when p squared equal to 0 at the end. But for now, assuming it's not equal to 0, let's see where that takes us. Then I divide both sides and I get y over p dp by dy plus 1 equals 0. I can transfer the 1 to the other side and write this as y over p dp by dy equals minus 1. Or separating the variables, I'm getting dp by p equals negative dy by y. Let me integrate both sides. If I integrate both sides, I get natural log of p equals negative natural log of y plus some constant which I'm going to write as natural log of c. So that gives me natural log of c over y when I combine using the rules of logarithm. Stripping the natural log from both sides, I get p equals c over y. However, p is equal to y prime. So I can write this as y prime equals c over y. Now I write y prime in its true form, which is dy by dx equals c over y. Separate variables once more, and I get y dy equals c dx. That can be easily integrated. So I'm going to get y squared over 2 equals cx plus some other constant c1. I'm going to not worry about this 2. So I'll make 2 other constants appear. So this gives me y equals plus or minus the square root of c2x plus c3. However, we have been told only to keep the y bigger than 0 branch, so we'll remove the negative sign. So the only solution is the plus sign. Now we have done all this assuming that p is not 0. Have we lost any generality in the solution because of that? As it turns out, no. Because the solution for p equal to 0 corresponds to saying y prime equal to 0. Well, that's easy to integrate. Y prime equal to 0 means dx by dy by dx is equal to 0, or the solution to that is y equals constant. However, y equal to constant is a special case of this solution. All I have to do is pick c2 equal to 0, and then I get y equals square root of c3, which I can call this constant C4. So I have not lost any generality in assuming that P is not equal to 0, since P equal to 0 is a inclusion in this solution. So this in fact is a complete general solution to that nonlinear differential equation. For your own amusement, I would encourage you to actually do y prime, y double prime, and substitute in there to make sure that it indeed satisfies it. A second technique, and another important technique of solving a nonlinear differential equation, is the method of separation of variables, which you have encountered in other contexts, like partial differential equations, for example. So suppose I have something like this: y prime equals y plus x squared. This is another nonlinear differential equation due to the presence of y squared. In fact, if you expand this out, you're going to get y squared plus 2xy plus x squared. It's a monster because it's dependent on y. If it just had this y term, it'd be linear, but it's got this y squared term that makes it nonlinear. This is actually a very famous differential equation in the history of mathematical physics. It's called the Riccati equation. And the special case of the Riccati equation is in fact the Bernoulli equation, which we're going to study in some detail. And also the Bessel equation is a special case of that. Amazingly enough, the Riccati equation, even though it's a first order differential equation, implies a second order differential equation, linear differential equation like the Bessel equation. So here's a general principle in ODE, in nonlinear differential equation theory. A nonlinear differential equation of low order equals a linear differential equation of higher order. So you can somehow sacrifice the order, make the order big, but in the process you'll be shedding the nonlinearity. So this very useful principle, advanced principle in differential equation theory, will be used in this course. But right now let's focus on this equation. How do we solve this horrible thing? Well, one way to do this is actually to make a change of variable first. Let's call y plus x equal to z. Then, where z is a function of x, remember, and primes refer to dy by dx, etc. So if I differentiate both sides with respect to x, I'm going to get y prime plus 1 equals z prime, which means that I can write y prime as z prime minus 1. Now that differential equation becomes something very harmless looking. It's z prime minus 1 equals z squared. Well, that is something that you give to a calculus student to do. So z prime equals z squared plus 1, and then you, if you like, you can separate the variables if you feel like doing that. So I get dz by z squared plus 1 equals dx, and if I integrate both sides, I'm going to get tan inverse of z equals x plus some constant c, and it doesn't look good to have inverse tangent, so we'll take the tan of both sides. So I get z equals tan of x plus c, and z, by the way, was x plus y, so I can write this as x plus y, which means that y is tan of x plus c minus x. So this is the full solution to the Riccati equation shown. The Riccati equation is not just this equation, it's a whole species of differential equations, of which this is one small member. Now this equation, I will spend maybe a couple minutes to show that this in fact solves the original equation. So let's find out what y prime is. The derivative of tan is secant squared. So I get secant squared x plus c minus 1. But secant squared minus 1 is tan squared. So I get tan squared x plus c, which is precisely equal to y plus x squared, is it not? Because y plus x, let's just do y plus x first. Y plus x is tan of x plus c, and therefore y plus x squared is tan squared of x plus c, and these two agree. So we have actually solved this rather forbidding nonlinear differential equation